Yet again, I neglected to mention something kind of important about this graph here on this previous example. So at the sharp turn here where we have ourselves a relative minimum, if we were just looking at the graph, does the graph change from negative to positive here? So it's decreasing and then it's increasing. Well, right here at the asymptote, the derivative, of course, does not exist, but you can see on the left side of it, the derivative is negative, meaning that your function is decreasing. And on the right side of it, the derivative is positive, meaning that your function is increasing. So the derivative does still, in fact, change from a positive to a negative right here at -2, indicating that you have yourselves a relative minimum. Okay, so let's go ahead and take a look at example 12, our final example here. Find the relative extrema of, and then we have ourselves a rational function, f of x equaling x to the fourth plus 1 over x squared. Okay, now then, where do we start? First derivative. And before I even take the first derivative, I'm going to rewrite this so that I don't have to use the quotient rule. I'm going to divide x squared into both of these things and get x squared plus x to the -2 power. There we go. And now we can just use the power rule and not have to worry about the quotient rule. So much easier. F prime of x is equal to 2x. And then minus, after we leapfrog that -2 down, -2x to the -3rd power. Okay, and then I want to clean this up. I don't want to have any negative exponents, especially since I'm going to have to solve this thing where it's equal to 0. I'm going to have to plug my test values into it, so I need to clean it up into a very convenient form. So, writing with a laser pointer, I'm going to factor out, first of all, a 2x to some power. Which power do I pick? This one's the first, this one's the -3. -3 is smaller, so that's the one that comes out. Okay, and then if I were to divide 2x by 2x to the -3, of course the 2's will cancel. This is 1 minus a -3, which makes x to the fourth. Right? And then, of course, you could distribute that to make sure that that makes sense. X to the fourth times 2x to the -3rd is going to make 2x to the first power. Yes? Okay. And then finally, minus 1 there. All right, and then we are almost done because now I just need to bring that x to the third down to the bottom. So f prime of x is equal to, this 2 stays, x to the fourth minus 1, all of this over x to the third. Yeah, there we go. Okay. Is this done yet? Yeah, okay. All right, then where are our critical numbers? Critical numbers come from the top equaling 0. So if I had x to the fourth minus 1 equals 0 equals 1, take the fourth root of 1 and you get positive and negative, just like square root. So plus or minus 1. Critical numbers. And then what about this bottom question mark? Do we get something for x equals 0? No, you don't. I want you to think about that for a second. Why is x equals 0 not a critical number? I mean, back here on this one, where the denominator was equal to 0, we got critical values. Why are we not getting a critical value in this case? The reason why is because if I take a look at the original domain here is x is not equal to 0. You already have yourself an asymptote here. So if you have an asymptote on your graph, there's no possible way that it's going to be a candidate for a relative minimum or a maximum. So be careful. All right, let's make ourselves a table of values for our first derivative test. All right. Our intervals include. Now, even though 0 was not a critical number, I'm still going to include it in the intervals because it's out of the domain. So our domain is essentially from -infinity up to 0, and then from 0 to infinity. So I still need to include that part in my intervals when I set them up. So from -infinity to, was it -1? Okay. And then from -1 to 0, 0 to 1, and then lastly from 1 to infinity. Okay, and then I'm going to put something special right here. This is unconventional. This is just probably something that I do. Put a little double line here indicating that that thing is, right, this one's an asymptote. Just to remind me that even if it switches from positive to negative or vice versa on either side of that asymptote, we're not going to get a relative minimum or maximum. All right, let's find a test value in each one of these. Negative 2 billion. How about negative a half, positive a half, and then a positive 2 billion? These things go, as they often do, into the first derivative to see if it's plus or minus. All right, so just out of convenience here, f prime of x was equal to, I think it was 2x to the fourth minus 1 over x to the third. Did I get it right? I think I did. Yay. Okay. So if I stick in a negative 2, that fourth power is going to make this thing a positive number bigger than 1. So this is plus up here, but the bottom cubing this negative is going to keep it negative. So positive divided by negative leaves it being negative, indicating that f of x must be decreasing on that interval. Stick in a negative a half. Negative a half here, it's positive. It's going to be positive, what, like 1/16 or something like that? But that's smaller than 1, so this is going to be a negative number up here and also a negative number down here whenever I cube it. So negative divided by negative makes it positive this time. And our function must be increasing. Decreasing to increasing. We found ourselves a minimum, a relative minimum. Okay, and then let's keep going, shall we? Sticking in a positive a half. Positive half is going to make this thing negative because that's smaller than 1. Smaller than 1 when I subtract is negative, but the bottom is positive. Negative divided by a positive makes negative. Decreasing. All right, let me stop for here for a second. So I can see I'm going from increasing to decreasing right there. So I should have myself a relative maximum here, right? No, you do not. Remember that thing is an asymptote. Asymptote. There we go. You don't have a relative minimax there. Okay. There's a black hole there or something. Let's keep going. We have only one more to do, and this thing is almost finished. Sticking in a 2. This 2 is going to be bigger than that one. That's positive. That's positive. The whole thing is positive. It's increasing again. Oh, it's nice and symmetric. Decreasing to increasing, we have ourselves another minimum. If we're going to justify, let's say at positive 1, f of x has a relative min at x is equal to 1 since f prime of x changes from, let's see, relative minimum, so it's got to go down, negative to positive. At x is equal to 1. All right, let's see what the graph looks like. Let me make sure I don't forget to show you that this time. So here you go. Whoa, along with its derivative, and you can see the asymptote right there at the origin, of course. And then here, our critical number, our in green, first derivative changes from negative to positive, decreasing to increasing. We have ourselves a relative minimum there. And then another one over here, derivative is changing from negative to positive, decreasing to increasing. We have ourselves another relative minimum, which brings us to the end of this lesson about how derivatives, specifically the first derivative, shape a graph. We can use the first derivative to determine the intervals over which our function is increasing or decreasing. Increasing, first derivative must be positive. Decreasing, first derivative must be negative. And then the first derivative test takes that one step further and draws the conclusion whether or not we have ourselves a relative minimum or a maximum at each one of those critical numbers.